Do all 45? It's all 45.
There we go. All right. So let's make sure that all works. All right. So let's go ahead and get started. Remember that your homeworks 3 and 4 are due at the end of class today. So make sure that you turn those in. Make sure that you get the attendance signed before you leave. Any questions before I get started? Oh, and someone else asked about the project. So that is due next week on Tuesday. If you want the bonus points, you can turn that in tonight before midnight. I know it says 4 on the thing, so it will be technically 5 minutes ago, but I'm giving you until midnight tonight to turn that in for the bonus points. Okay, question? No, I do not. If you have some sort of really, really good reason, like, oh, I got in a car crash and I'm in the hospital, that's fine, but otherwise, no. Question?
Will there be like other homework on top of the project too this week?
Yes, so there should be some homework on substitutions, which is what we'll cover today. Anything else? Yeah, so think of the projects as being extra on top of your homework. All right, we ready? All right, so today we're going to talk about homogeneous equations. And basically we're starting our talk, our dive into substitution. So this will be today and Thursday we'll talk about this sort of thing. And then we might talk about one final kind of substitution on Tuesday if we don't get to cover all of it. All right, so let's get started. We're going to talk about substitutions and then these two different kinds of equations where they apply. All right, so first off, what is a substitution? So you kind of know the idea, maybe you've seen it with limits or definitely with integrals where you do u substitution to make the integrand look simpler. Let me make sure that I am. 1 sec, I just realized I might not be recording that. Okay, yeah, I am. I had the thing muted. Okay, so you know about u substitution. And then you can also do this with differential equations to make them look simpler. And okay, you've actually already done that too, because computing antiderivatives, which you do all through Calc 2, is a simple form of solving differential equations. You're solving differential equations where you just have derivative equal to a function of x. Now you just have function or the function on both sides of the equation sometimes. All right, so here's an example. We want to use the substitution u equal y over x squared to solve this dE. Okay, so what do we do? So there's a direct method, and it's a process written out here for you, which we will go through, but you want to take a differential equation in this standard form that we've seen already for first orders. And then you have some function of x and y that you're using to define a new variable. Right? So what you do is see, all right, well, usually you can solve that for y. This gives you a way to plug in something for y to only get x's and v's. So you're sort of creating a new differential equation like this. And then you compute dy dx so that the dy dx can also be substituted. Because you need to have no y's in order to create this new differential equation with only one independent and one dependent variable. All right, and we'll see how this works yet again. And you want to replace all instances and then solve the differential equation that you get. Hopefully it's simpler or is writable in a nicer form. or an actually computable form, and then substitute back in once you have v as a function of x, and then you can solve for y. All right, so let's see how this works with this example. If you haven't finished copying, don't worry, we'll walk through it. So we have the differential equation, y prime equals 2y over x plus, and then I forgot what I wrote there, cosine squared y over x squared. All right, and then it says our substitution should be this thing, v equals y over x squared. All right, so step one here is solve for y. Y equals x squared times v. So a lot of writing on the previous slide, but really it's just saying solve for y. All right, step two. Compute y prime. And actually, let's do this a little further over. Y prime using this expression. Okay, well, think of v as being dependent on x. So v equals v of x here. And so we want to do a product rule. F times g, and what's the derivative of that? It's f prime g plus f g prime. Okay, so we can fill that in. Derivative of x squared is 2x times v. And then x squared times derivative of v with respect to x. Okay, so there's y prime, and we have y, and now we want to substitute all of that into our differential equation. So we have 3 substitute. So y prime is all this stuff, which we can just copy here. And that's going to be equal to the right side of the equation, but with y substituted with x squared v. So we have 2x squared v over x plus cosine squared. And then remember, our original form for v was y over x squared. So this is just cosine squared of v. Is that where we wanted there, really? That seems odd. Oh, okay, yeah, that works out. Okay, so now the x cancels out over there. And we have, all right, step 4, we're going to solve this differential equation. Two xv plus cosine squared v for v. Solve for v. All right, well, we get some cancellation on the left and right sides. The 2xv cancels out. And we're left with a somewhat simpler differential equation here. Okay. Plus cosine squared v. Someone want to let me know what kind of differential equation that is? Classify it, and then tell me if we know how to solve that kind already. It's first order. What else? It's not linear. It is separable, yeah. So it's not linear because we have cosine of v, which is the dependent variable. It is first order because we only have the first derivative, no second derivatives. And it is separable because I can do this. So write v prime as dv dx, and then we get dv over cosine squared equals dx over x squared. And now we can take the antiderivative of both sides. All right, so, oops, sorry, hopefully that doesn't die. So we have antiderivative secant squared v dv equal antiderivative 1 over x dx. All right, and we can do those two. So the antiderivative of secant squared is, oh,
Nope, sorry.
close. Nope. There is a tangent in there. It's tangent. Yep. Yeah. Here's a quick rule. Yeah. Secant is.
Yeah.
So derivative of tangent is secant times secant, and derivative of secant is secant times tangent. So you swap the first and the last, and you get another identity question. Right here. So I divided both sides by x squared, and I divided both sides by cosine squared. That's how I get this and this. And then I took v prime and wrote it as dv dx, and that allows me to multiply both sides by dx. So now I have dv over here, dx over here, and then all of the x's and v's are separated. Okay, so we have tangent of v equals, and then antiderivative 1 over x squared, remind me? Negative 1 over x, yeah. And then plus our constant of integration. Okay, well, that's v, and actually tangent v. So maybe we should solve for v. Let's see, v equals arctangent of negative 1 over x plus c. And then, wait, v was writable in terms of y. So this is really y over x squared. Oh, well, that's pretty easy to solve for y. Y equals x squared, arctangent of minus 1 over x plus c. And so there's our general solution. Okay. Questions about this example? Method fairly straightforward. So there's also an indirect method. And in this case, we are not going to compute derivatives of y, we'll compute derivatives of v. We want dv dx as a function of x, y, and dv, dy dx. And the reason for these two different methods is that sometimes the form of the substitution that you use is easier to compute derivatives of one way versus the other way. So if you look at the substitution right here, v equal xy squared, that has a much nicer form to solve or to take a derivative of when I have v written as a function of x and y than if I solve this for y. Because if I solve this for y, it looks like what? I get y equals plus minus square root of v over x. And that's going to be pretty awful to take a derivative of, isn't it? Yeah, I need to take a derivative of the square root and then chain rule and multiply that by a quotient rule, or one of the functions is undetermined. So it's not going to be fun. This is hard. Harder than it needs to be, really. All right, so here's our example. Let's go ahead and try to solve that. And I didn't give us space, darn it. Clean that up, and then we can do that same example right here. So d y dx equals, I said 1 over y minus y over x. Okay. And then we have the substitution v equal x times y squared. So help me out with this one. So my first step is compute dv dx as a function of x, y, and y prime. So dv dx should be what? So I'm going to use what derivative rule to start? Product rule, yeah, because I have function of x times another function of x, because y depends on x. And so we get, right, 1 times y squared plus x times 2y, and then what? Y prime. Don't forget that chain rule right there. All right, so this is y squared plus 2xy y prime. That looks a little complicated. Okay, well, what's our next step? It says, in the resulting formula, replace y prime with the differential equation, or whatever the differential equation says. So, 2, here's what I just got for dv dx, and I have y's and y primes in there. I have something that I can solve for y, and I have something that I can plug in for dy dx. Okay, so let's go ahead and do that. So dv dx equals, all right, y squared. All right, well, that's v over x from up here. V over x equals y squared. All right, and then plus 2x, and then y, well, that's square root of v over x. All right, and y prime, let's see, y prime is 1 over y minus y over x from the differential equation, right up there. And wait, we've got some y's in there now. And let's see. Oh, maybe I jumped the gun on substituting for y there. Because what happens if I do this? Stuff cancels out, yeah. So I multiply it through and I get v over x plus 2x. And then 1 minus y squared over x. Okay, and then that y squared, well, that's v over x. So we get, finally, v over x here plus 2x minus 2x v over x over x. All right, we do some more canceling. To get this. All right. And so now we have something that hopefully we can solve. Can we solve this? Maybe we should combine some stuff first. 3v over x plus 2x. So, all right, help me out again. What kind of differential equation is this? Classify it so that we can decide whether we know how to solve this or not. It's linear. It's first order, it's linear. Yeah, okay, that's all we needed. First order and linear, so we know how to solve this. And in order to do that, we need to write things on the other side, right? And we write 3 over x times v equals 2x. And now we find our, what's that thing called? Not p of x. Well, maybe, yeah, you can use that. But what's the final thing that we want out of p of x? Mu? Yeah. What is that called? Integrating factor. Yeah. Mm-hmm. Well, you knew it was the mu. All right, so mu equals, it's this weird formula, e to the integral of, and now p of x, which is -3/x. Yeah, don't forget the minus there. All right, and that should give us 1/x cubed. If you want, you can work through that, but question?
I don't know if my glasses are just bad, but
I may be writing too small.
it says minus 2x over x over x plus 2b over x.
Sorry, I missed that last part.
So in the first, like, b over 2x equals b over x 2x over x.
Yeah.
And then we simplify the 2x b over x over x b over x. But it's subtracted in the first.
Right. So you see what happens is thank you for catching that. That makes our integrating factor a little bit nicer. So now we have plus 1/x. Yeah. So our integrating factor is then actually just x. Okay. So we have a much nicer integrating factor there. And if we multiply through by it, we get u of x. We get x v prime plus 1v. And that's equal to 2x squared. Now we integrate both sides and we get x v equals 2/3 x cubed plus c. Now we have, okay, well, x times v, v was x times y squared. And so we have x squared y squared equals 2/3 x cubed plus c. And sometimes it's a good idea to leave things like this. If you end up with something where y is squared, it usually means that the solution is not a function. It means it's a couple of functions sort of glued together in the xy plane. Because when you take the square root of this, you're going to have a plus root and a minus root, correct? So one of those will be an upper version of the function and the other one will be a lower version. If you want, though, you can go ahead and solve this for y and write plus minus the square root of 2/3 x plus c over x squared. Just don't forget that plus minus right there if you do that. All right. So that's a couple of substitutions. Questions about how these work? V was given to us in the problem. Yeah, there are some ways to find V for certain kinds of problems. Generally, it's going to just take some cleverness to find something that works. No, sometimes there are classes of problems where a specific type of substitution works, like the integrating factor, actually. There is another kind of differential equation where a similar kind of integrating factor works as a substitution. And then there are other kinds where there's a formula for finding a substitution. Mm-hmm. I'm not sure how much further along in the course those are, though. Sorry, one more time. Step one. So for step one, I just took this change of variables right here, this equation defining it, and I took the derivative of both sides with respect to x. Yeah. So that's why I did a product rule over there and just left this as dv dx. Okay. Anything else? All right. So that's our indirect method. What's next? So now we have a class of differential equations that we want to use substitutions to solve. So a homogeneous differential equation, this is a different homogeneous from the kind that we talk about for linearity. It's one that can be written like this, where y over x is, you can have y over x kind of written as one variable on the right side of the equation here. And so if we look at a couple of these things down here, those are some examples of what these might look like. So here you have dy dx equal to, well, if I were to multiply all this through, find a common denominator, it would look pretty ugly. But when I leave it written like this, and maybe if I black all that stuff out and just write it as u now, or v, I guess. Oh, now that just looks like a very simple polynomial function. So that's the idea here behind homogeneous differential equations. Right. And then you see the G over there. That's not supposed to be there. Okay, so let's do a little bit of practice. Can you recognize which of these differential equations are homogeneous? So I will give you one more tool before I force you to practice this. If you have f of xy on one side of your differential equation, and you substitute t times x and t times y, or just some variable t, if this ends up being exactly equal to f of xy after you do some algebra, i.e. the t's cancel out somehow, then it's a homogeneous differential equation. Okay, so that's another way to recognize it. So I'll give you a few minutes to go ahead and practice that. See if you can figure out which of these is and is not homogeneous. And then we'll come back and do it together. So let's say, how much time do we have? It's 4:31, so let's come back in 4 minutes, 4:35. It's somewhere around there.
No, I'm just saying that. No, yes. For sure. So we got the sum of y over the 2 divided by 5. I'm going to use the substitution. I realize he's farming. You will be satisfied as an addition over here, where this is kind of the left. This is sure. The bottom right actually, I think, was. No, right. First square.
Little F is absolute.
I don't know.
All right. So let's go ahead and give these a shot. So what do we think for that first one? Is that homogeneous or not homogeneous? No? Okay. Was that a yeah for a no? Okay. Well, let's check. So a couple of you asked questions about this, so it's probably good for us to work through it a little bit at a time. So this thing on the right side, this expression is what we're calling capital F of xy. Right? This y squared plus x, which is in the first one for a second. If I take that and, not x squared, I replace every instance of x and y with t times x and t times y, then I get, that should be ty, y squared plus tx. All right. Now, does the t cancel out and give me back y squared plus x again? No, it does not. So t times ty plus x. All right, if I choose t equal to, I don't know, 1, oh, that should be y squared. Then I get, well, let's see, y squared plus x. Okay, so for t equals 1, it works. Okay, that's obvious. It should work for t equals 1. What if I put t equal 2 in there? Then I get 2 times 2y squared plus x, and this is 4y squared plus 2x. Oh, that didn't scale the way that I wanted it to. Okay, so this is going to be non-homogeneous, right? It's not the same function for every value of t. It doesn't look the same on the right side here. Okay, so no, this one is not. So non-homogeneous. All right, what about that second one on the right side? dy dx equals sine y over sine x. You think it is homogeneous? Anyone think it's not? Okay, let's check. So actually, let's leave that up and then we'll do it over here. So sine of t times y over sine of t times x. All right, do I get to factor constants out of sine? No, it's not a linear function. So this is not equal to sine of, or I don't have space for that. This is not equal to t sine of y over t sine of x, which would be great because then the t's would cancel. But because the t's are stuck inside of that sine function, they don't. And it's not homogeneous. So, no. This one is also non-homogeneous. What about the second one? X over y, or sorry, the third one, not the second one. Yeah. So this one is even almost exactly written in the form we wanted it to be. 1 over y over x. And now if we go back to the actual definition of homogeneous differential equations, this is some function of y over x. Our function g is 1 over v. And if we go through our substituting with t method, then we have t times x over t times y, and the t's clearly cancel out. So we end up with x over y again. Okay. So this one is, yes, homogeneous. What about the next one? dy dx equals y over x plus 1. I'm going to say this one is not homogeneous. And it's that plus 1 down there that causes us problems. If we put tx and ty, well, the t's don't get to cancel, do they? So that one is non-homogeneous. All right, and then how about this one? It is homogeneous?
Yes, that's nice.
Yeah, okay. And we say it's not? Okay. Why do you think it is homogeneous?
So it's natural log y over x.
Yeah. And then you have g of v is just log of v. All right. So that one is homogeneous. And then this last one, well, that looks pretty awful and like it might not work. So that is a reverse of the keep, change, flip rule. If you have 1 over a fraction, this ends up being b over a, because you keep, change, flip the a and the b. I just did it backwards. So I saw b over a and wrote it as 1 over a over b. All right, so now this one looks maybe a little complicated, but now if we factor out x squared from everything, what happens? Well, I get x squared 1 minus y squared over x squared times 1 plus y squared over x squared. These cancel, and now that is y over x squared. So g for this one, I'm running out of space, is 1 minus v squared over 1 plus v squared. Okay, so that one is homogeneous. So how this substitution works. So if, here's a shortcut, a theorem, if this is a homogeneous DE, then the differential equation you get out as a result ends up being separable. And it's always separable. Why? Oh, let's prove it. So let's take my differential equation, dy dx, and since we know it's homogeneous, I can write it how? As g, some single variable function of y over x. A single variable function where I plug in y over x. All right. Well, given that, if I apply that general process, the direct method or the indirect method that we did in the first couple examples, we get, all right, v equals y over x, y equals xv. All right, let's take the derivative of maybe this one, because I don't want to do quotient rule. So y prime then gives me v plus x times v prime using the product rule. Okay, and then on the right side, I just have v, or g of v. So when I substitute, I get this differential equation in v and x now. Okay, well, let me do a little algebra, move things around, and actually I'm going to write that as dv dx now. G of v minus v. This is a single function of the variable v now. There's no x's. V depends on x, but it doesn't show up directly there. And now, divide by x, multiply by dx. And on the right side, I get dx over x. And then if I divide by everything over here with the v's, I get g of v minus v. And this is separated or separable. We have all the v's on one side, all of the x's on the other. And so now we can integrate both sides. And so our solution ends up being antiderivative 1 over g of v minus v dv equals log absolute value of x plus c. All right, so for homogeneous DEs, that substitution always makes it separable. You guys still need this slide? All right, so here are a couple of examples. We want to solve this IVP. First off, is it homogeneous? I would hope so because we're in the homogeneous section, but let's check. So we've done this already. This is our f of xy. If we look at f of tx, ty, we get, what do we get? T squared xy minus t squared y squared over t squared x squared. Does that cancel out? Yeah, because I can factor out t squared here. And then it cancels with the 1 on the bottom. So yes, this is homogeneous. All right. Well, that means that I know what my substitution should be. So I'm going to take this differential equation and use the substitution v equals y over x or y equals x times v. You choose whichever one you want to use. I think that often this one tends to be easier to work with. So let's do that. We know dy dx ends up being v plus x times v prime. Okay. And then over here, well, oh, I haven't written that as g of y over x, have I? So let's try and do that before we keep going. So this is, if I cancel, let's say I split the fraction here, and I divide each term by x squared, I get y over x minus y over x squared. And so this is v minus v squared. And so we get this thing equal to v minus v squared. Okay, well, we get some nice cancellation there. The v's go away. And then I have dv over v squared equals minus dx over x. And if I take the antiderivative here, I get minus 1 over v equals minus log absolute value of x. Don't forget your plus c there. And then what's 1 over v? Well, I come back up here. I see, all right, v is y over x. So 1 over v is x over y. All right, so moving that up here, we have minus x over y equals minus log absolute value x plus c. And last thing is I need to solve for y. Swap these two. So I get y equals minus x over minus log absolute value of x plus c. And if you want to get rid of the minus there, you can do that. Distribute it to the bottom part, and then the c will absorb the minus. Okay, so there's our general solution for that differential equation. And we used our homogeneous substitution there.
The v minus v squared equals y over x minus y over x squared to the dv over v squared part.
So I was able to cancel these v's with no powers on them. And then I have minus v squared left over here. So I divide by v squared. And I have x times v prime over here. And so I divide by x in there. All right. Now, are we done? It's good that we found our general solution, but what are we solving? Yeah, we have an IVP, so we have that initial condition that we need to check. So y of 1 should equal -1. All right, well, y of 1 is 1 over natural log absolute value of 1 plus c. That's 0. And so c equals -1. And then that tells me that my actual solution is log x -1 here. Okay. And so there is my actual solution with that initial condition. All right. We've got one more example and then another type of substitution, and then we'll be done. So we want to find the general solution of this differential equation now. So this is written in a slightly different way than we're used to, where I have the dx and dy already separated. This form is usually used for exact and inexact derivatives. And we might do that later on if we have time. Otherwise, we'll just do the substitutions, because you can use the substitutions to solve those sometimes as well. Okay, so, all right, I'm in the homogeneous section again. I want to check, is this homogeneous? Well, I have to write it in the correct way, right? So first off, I need dy dx equal to something. Well, that means I have to divide both sides by dx. All right. And then on the right side, well, okay, here I have minus x squared equals minus that stuff, so minus y squared plus xy plus x squared. Minus goes away, so I can ignore that part. And now I can divide both sides by x squared. And we get what on the right side? We get dy dx equals y over x squared plus y over x plus x squared over x squared is 1. And this is one of those examples way back at the definition of homogeneous. So let's go ahead and solve this now. Substitution. You want to use v equals y over x or y equals xv. We kind of used both last time, didn't we? So here, we can just use that this is v directly. And then over here, when we take derivatives, it's easier to use this one. So you're allowed to use different formats for that change of variables. Same way that you do u substitutions for integrals in different ways, or you can do like back substitutions and stuff. All right, so dy dx, we know that that's going to be v plus x times v prime. We've seen this a couple times now. So our differential equation ends up being v plus x v prime equals v squared plus v plus 1. All right. Yet again, the linear power of v cancels out. And we get x dv dx equals 1 plus v squared. And as the theorem says, this is separable. Bring all of this stuff to the other side and bring the x down there. What does this look like? dv over 1 plus v squared equals dx over x. antiderivative both sides. What's the left side? Some of the special ones that we should know. Not ln. Arctan, yeah. So this will be arctangent of v equals, and then yeah, ln on the other side. Sorry if that's what you were going for. All right. And then last things last, we want to solve for y. So we have v equals tangent of all of this stuff. And we know what v is. So we have y equals x times tangent log absolute value x plus c. All right. Are we done? Yeah, we have the general solution. No initial conditions were given to us, so we don't have to keep going. All right. Questions about these so far? So we're going to move on to something slightly new next. Okay. All right, so last thing is these linear substitutions. And here's our motivation. So there's usually a right substitution if a substitution is the right method to go for. There's usually a choice that will make things easiest. Because sometimes you can choose all sorts of different things for U substitution. In Calc 2, one of them will work better than the others. Same thing for differential equations. All right, and in this case, turns out that something that looks like this is easier for this one. Now, why would it be that and not the whole thing here, or x minus y plus 2? Well, it could be. Those might also work, but that's relatively simple. It avoids adding extra constants on, and so we might as well have something that looks like just a combination of x and y if we can get away with it. Okay, so I think I'm going to leave this one to you for about 4 minutes. So give it a shot. Try to use some of the tools that we've already worked through. The substitution is slightly different, but the methods are more or less the same. Give it a try, see where you get.
But I got some deep. So you got -1 plus 1 plus 2. Should be negative. Because v equals x minus y. Yeah.
Keep trying.
Oh, yeah, so why we have. Negative v minus 1.
Oh, that's why it's hard. But it's so stupid.
You forgot.
Oh, you're right, you're right.
I never forget.
All right, let's go ahead and give this one a shot. Did you guys get anywhere? Halfway? Okay. Did you get through the substitution at least? You get the differential equation in v and x? Almost? Okay. Good. Sounds good. Do I have an extra page here? I do. All right. So let's go ahead and give this one a shot. Last few minutes here. I know we're all tired and want to go home. So we've got dy dx equals y minus x minus 1 plus 1 over x minus y plus 2. And then we're given a substitution, v equals x minus y. Okay, well, I see v right here immediately. And then over here, this almost looks like it, but there's an extra minus sign. So that's minus v. And the right side ends up giving me minus v minus 1 plus 1 over v plus 2. Okay, so that's the easy part. What about dy dx? V plus xv from, oh no, this came from yeah, this formula was specific to that substitution for homogeneous equations. Yeah, so this one does not work for this case. No, I understand how you can make that mistake. I think I've done that before. So usually when you have a new substitution, the easiest way to go at it to get the derivative is just take the derivative directly. So here we'll get dv dx equals 1 minus dy dx. Okay, and so now we can go ahead and solve for dy dx and then just substitute that back in. So dy dx equals 1 minus dv dx. And that's what we'll put over here. Okay. So now we can go ahead and start simplifying. This looks like it'll be separable. Is it? I don't know, maybe. So we've got, let's see, So let's subtract 1 from both sides. That'll make this a -2. And then if I multiply everything by -1 to get rid of the minus there, I'll get v plus 2 minus 1 over v plus 2. All right. And then, well, okay, let's combine fractions here. This is really v squared, v plus 2 over 1. And so that'll give me v plus 2 squared minus 1 over v plus 2 if I find a common denominator. And now this is a function of just v. There are no x's that are appearing anywhere else, so this is separable, and we can write it as v plus 2 over v plus 2 squared minus 1 dv equals dx. And then take the antiderivative of both sides. So on the right side, we get x plus c. And then on the other side, we have, how do I do that? U substitution? I think substitution is probably going to be best. I'm just trying to think of what's easiest to choose here. Let's choose the whole thing down here as u. That means that du is 2v plus 2 dv. Yeah, my chain rule doesn't do anything now. So if I then insert a 2 right there and compensate for it with a 1/2 out front, then on the right side, up here, we get 1/2 antiderivative of du over u, because I chose the entire denominator as u, and that's 1/2 log absolute value of u. All right, last thing we need to do is substitute everything back in. So we get y's and x's. And u was all of this stuff. So we have x plus c equals 1/2 log v plus 2 squared minus 1. And then v was x minus y. So we can go ahead and plug that in here. X minus y plus 2 squared minus 1, and that's it. If we want, we can go ahead and try to solve this for y. It's the practice of our algebra skills, so why not? So multiply everything by 2, and then use this to raise base e. So now we have absolute value x minus y plus 2 squared minus 1. And then remember, whenever you do this log thing, or this thing where you cancel out the log and you have that absolute value there, remember that we said it's always a good idea to bring the c down and now just write it as a single constant c. Because now the plus minus from the log is accounted for in the sign of your choice of c. Right? And swap that around. And now we can go ahead and solve for y. I have plus 1 to x. And then take the square root of that. And that's equal to x minus y plus 2. And finally, add y to both sides and subtract that. So we have y equals x plus 2 minus plus root 1 plus c e to the 2x. There's our general solution. Okay. I had a theorem here that I wanted to cover, but we will, it just says that you can turn this into a separable equation. So it's the same as before, and we'll come back and do some more stuff on Thursday. Thank you.